Class gets out at 6:50. We won't finish all of this, which is fine because we don't have to. Oh, this is a much nicer document camera than the other classroom. Very exciting. You guys are winning and you don't even know it. Let's see. Okay, so this is section 1.1. It's titled "The Counting Numbers." What is this crazy talk? What are the counting numbers? What does that refer to? Can anyone tell me? Candace, what are the counting numbers?
Like 1, 2, 3, 4.
Very nice. Yes, I like that proper use of infinity. So the counting numbers really are the numbers you use when you count stuff. So who cares? Why do we need numbers? Why are they important? How many of something. That is so true. So if you think about the Earth throughout history, how long, and the people, not just like the dinosaurs, but like when it had people, how long did it take for numbers to show up, you think? Who said it? What was it?
A second, a day.
Yeah, like very quickly, because when you're out foraging for fruits and nuts, it's like, oh, is that 1 nut or 2 nuts? Like you very quickly start counting things, right? Because if you have 2 nuts and your neighbor only has 1, you're like, yes, I'm going to live through the winter. So numbers and counting happened very, very quickly when people started, I don't know, rationalizing. And it's not just people, because they've done experiments with really really smart animals like ravens and I don't know what else. But they can count as well. They will, if they are offered something delicious and they are offered 2 of the thing or 5 of the thing, they will know that the 5 is more. So it's not just people, but I don't think that ravens are writing books about it. But pretty important, a pretty big deal. Let's see, where do I want to put this? Let's put it here for now. I need to write down some of these interesting things that you all have been saying. Here's Candace. She says, numbers we count with. And she even gave us an example. She said 1, 2, 3, and she went all the way up to infinity. And then why are they important? Because we are going to be able to quantify how many of something that we have. That was the very earliest usage of mathematics, which if we get to the videos today, that's what one of the videos talks about, is the early days of numbers. You to quantify. The amount of whatever you're counting, I don't know. Whatever you need to keep track of. And you can imagine that's a big deal. Probably in just a 1 day of your life, you're quantifying things like how many miles before I run out of gas, and how many, cans of soup do I need in the store this week. All day we find different ways to quantify things that we are doing. The counting numbers are known by a different name. Does anybody know the other name for the counting numbers? Starts with an N. Starts with an N. They're natural numbers. They're very natural. Natural numbers. I'm not sure why it's called that. I think it might come from French. I don't think it started in English, but it got translated into the natural numbers. So the counting numbers are also known as the natural numbers, and they have a symbol. It is that N that I put there. But it's not a normal capital N, it's kind of a fancy one. which if you see it in a book, it's kind of fancy. So I try to make it fancy by putting a double line here. It's not just because I'm bad at writing, but it's supposed to be a fancy N. So natural numbers, fancy N, are also the counting numbers. When you're dealing with small children, usually you call them the counting numbers because they know what counting is, or they've heard the term counting. Usually you wait till you have some older students before you call it the natural numbers. But at least you guys know that it's either or is fine. I'm going to put the counting numbers on my chart paper here, and I'm going to save it, and I'm going to be adding different subsets of the real numbers until I've collected all of them. So it's going to take, I don't know, maybe by next week we'll have them all on here. It's actually the first question in your homework, is what's going to be on this chart paper. So let me find a better marker. I think I tried, it's nice to try to color code this. So I try to do, this is blue. So there's different ways you can do this. Maybe, I want to do a rectangle. How do you guys feel? Do you guys feel like quadrilateral, or do you feel like a circular shape? Does anyone have a feeling today? Circular. Well, it's not going to be a circle. It'll be some kind of oval. I shouldn't say oval because the proper mathematical term is ellipsis. But we're going to put my counting numbers in here. So on your paper somewhere, put counting numbers and put a circle around it. Or some kind of something around it. It could be a quadrilateral. It could be a rectangle. Hope I'm not writing on the wall. Oh, good enough. So pretty soon we'll have all the real numbers. Right now we only have the counting numbers represented. Do you want me to give one to you?
No, that's fine.
Could you smell it from there?
No, I smelled her white out.
Oh, I thought you were smelling my marker, which I smelled and it was delicious. Do you guys know the famous person that invented whiteout? Well, it's because you were, in the 90s when Friends was on TV. I think Matthew Perry, the actor, I think his mom invented whiteout. She was, I think, a secretary and she invented whiteout. Now you know. Why is he acting? He has all that whiteout money. Just sit around. Okay, so there's two different ways. There's two different ways to think about the counting numbers. One way is as an ordered list. The other way is to tell how many, which is something that we had above. To come up with some quantity of whatever you're measuring. The counting numbers or the natural numbers, it really is an ordered list. It is not just a list, but it has a particular order. Because what happens as you go from one number to the next when you're counting? It's bigger by how many? One. Wow, that is correct. There is a pattern to your natural numbers, to your counting numbers. It is a list, but it's a list that has an order. You say them in a particular order because it means something. It means you're adding another one, you're increasing by one. It's like, not like the alphabet. The alphabet is a list, but I don't know why we say it that way. You could say it a different way, it would still be the alphabet, I guess. There's no need for the alphabet to be said in a particular way. It doesn't do anything to it. But the counting numbers is special. That is a list, but it goes in an order. And the order has meaning. And then we use those counting numbers, of course, to tell how many of whatever it is we're counting. And the second way, the telling how many, I guess because it's such a big deal, it has its own fancy name that goes with it. This fancy name was, it was definitely on a test last semester. I don't know, I think it appeared more than once. And people like to forget it because we don't talk about this much. But the fancy name for telling how many, I've already lost my marker. Does anybody know what it is? It starts with a C. You might be surprised. It's called cardinality. Cardinal, like a cardinal, cardinality. Second way is called the cardinality of a set. So if you're a sheep herder and you're counting your sheep, in ancient times you would be finding the cardinality of your sheeps, whatever your set happens to be comprised of. So that word cardinality, I would ask students, find the cardinality of this group of things, and they would remember what the word meant. And all I had to do was count the things. So I encourage you to remember what that word means. Remembering it was on the first test, and then I think it was on the final. Anyway. This word's subitizing, I think is how you say it, subitizing. I don't hear a lot of people saying it to me, but I think that's how you say it. Does anyone know what this word means? It's gotten trendy in math education recently. I don't know why. You might think so, right? I got my PhD with a guy who now works at ETS. ETS is, it's in a few different places, but they make like the GRE and they make a lot of standardized tests for different things. And he talked to me once, he called me once last year and he got very excited about this word because he just learned it. I don't know where he came from. I'm like, yeah, this is very trendy. I'm surprised that you just found out what this word means. So, you've all done it, I think. Eventually, kids will do it too, but it might take a while. So subitizing is referring to, if you're finding the cardinality of a set, you're telling how many you have without actually counting each one at a time. We don't always, especially as we grow up, we don't always count every single one of whatever it is we have. Does anyone have an example of where you might have done that? Good. So you might look at the shape that the dots make. Those dots are called pips, I think. What was yours?
So would it be like at work, for example, I cut material, right? So let's say that I need like 100 pieces. They're all squares, so usually I do like 10 and then 10.
So you make an array out of them?
And then
So,
I just
yeah.
do 10 and 10 and it's all 100.
Yes.
Can you say like you need a couple or a few? Is that the same thing or is that something different?
That's just different ways to say two.
Okay.
This is counting a collection of things without actually counting every single one. So
like
usually it's
tally
because they're in a particular layout.
Like tally marks, like kids just
Like
figure out
tally
that's
marks,
like,
maybe, yeah.
That's so fun.
Sometimes we're using the principles of multiplication when we do it, just because of how things are organized. I can remember. Does anyone have any other thoughts about something else? Yes.
I was playing Monopoly with my friend, and he just like how there's 10 on each side. Like you just jump, and I was like, you didn't even count. He's like,
Oh, I like him. Is he in this class?
No.
Good. So using what he knows about the two numbers that add up to 10. Maybe. The thing that it reminds me of is when I was a very young kid, I would watch my family play cards, and I was too young to play. And then when they finally thought I was old enough, I remember being very deliberate about counting the number of dots or whatever, hearts on each card, because I was young. And then eventually you don't have to do that anymore. You can add the numbers together without being very literal about counting them all. And sometimes with cards you use the layout of the shapes. Back in old-timey playing cards didn't have the numbers on them, they only had the pictures, so I guess the numbers are for people like me.
This is more like third grade when they're multiplying, like you said, the arrays. Like when the kids figure out that's like 3 rows and there's 6 in each, so they know there's.
Yes.
That's when it clicks. Okay.
Yeah, I think that's when we start getting better at
Like
doing
when
this.
it did the.
Anyway, so that is, something you'll probably see around because, like I said, it's getting very trendy in the last few years. That clock keeps moving. Okay, one-to-one correspondence. A correspondence is like a pen pal. And, right? That's what a correspondence is. Does anyone have any thoughts about what a one-to-one correspondence is before I spill the beans? touch it, and what do you do with it? Why are you touching it?
Number, count 1, 2.
So you're touching it and you're assigning a counting number to it. That is lovely. Yes, that is a one-to-one correspondence. You're assigning, or you're creating a relationship between each item and a member of the counting numbers. I didn't say that as good as I hope I will write it down. But yes. I was using this, you know, I like to use all these terms in my regular life. So my husband was telling me how his work is doing inventory because, oops, linking an initial. My husband's work is doing inventory because it's the end of the year and he's complaining about certain people that can't count their stuff, I guess, accurately. And I said, oh, they're having a problem making a one-to-one correspondence between their stuff and the counting numbers, right? He was like, oh, brother. So, but I mean, it happens all the time. Every time we count things, we're creating a one-to-one correspondence.
So if they have 5 blocks, and if they're not going in order, but they are doing 1, 2, you know, but if they start doing 1, 2, 3, you know,
Well, yeah,
how
they
kids
can
do
they
that?
can do that in
So
whatever.
it's still 1 to 1.
That's still a one-to-one correspondence. That's a very good. We're going to see an activity that will show us examples of that. Probably not today, but I don't know. Okay, I need to finish writing. An initial portion, it could be a long portion. Candace told us the counting numbers are infinite, so hopefully we won't be counting to 1,000,000 and assigning 1,000,000 to a group of objects, but it could be, you know, a significant collection of numbers here. That's the counting numbers that we need to assign. I don't know. It depends what we're counting. So whatever you're counting, each of those items gets a value that corresponds to, of course, the counting. Yay! Yay! And now you might be thinking, why are there birds on this piece of paper? And you might be thinking, you know, just counting things, like, you know, really little kids count stuff. So what's, like, how big a deal is this really? Like, you know, is anyone taking this into consideration? Do we need big words to describe this process? Well, actually, the idea of making one-to-one correspondence is actually a big deal. If you took Algebra 1 in high school, or if you took college algebra, the whole concept of functions is based on making a one-to-one correspondence with a set of values here and a set of values over here. So it actually does go on in the future, the idea of making a correspondence between different things. This is trying to illustrate a pretty famous mathematical principle, which is right here. It's called the pigeonhole principle. You can actually find mathematical documents that use this principle. I'm not making it up. The pigeonhole principle. So you have n items and m containers. So in our example, the n is pigeons, the number of pigeons, and the m is the holes that you're going to put them in. Imagine you got invited to Mike Tyson's house and he has his pigeons. I think that's what he collects. And he's going to talk to you about all of his pigeons. So n is the number of pigeons, m is the number of holes. Maybe those are their little hidey holes. And you're putting a pigeon, making a one-to-one correspondence between pigeons and holes. So we got one here, one here, one here. Very attractive. One here, and one here. These ones look like twins. One here, and oh dear. What happened over here? There's 2 pigeons in the same hole. I do not have a one-to-one correspondence between pigeons and holes because I have more pigeons greater than the number of holes that I have. So the principle is very rudimentary. It just says, yeah, if you have more pigeons than holes, then one of your holes has to have more than one pigeon in it. And this is used in different mathematical proofs for different things that people want to prove. I didn't bring any of them with me. You might have to just take my word for it. So it is something that starts very, very young with very small children, but it carries on to all different kinds of mathematics, the idea of forming a one-to-one correspondence. Yay. Okay. Any questions on that page? Guys, it's happening. We did our first page together. 500 more to go. Probably not that many. Okay. So we're going to kind of look more at the counting numbers. Sorry. We're going to try to look more at the second definition here, the thinking about the cardinality of a set, because that's something we expect our students to do, especially if they're small, and that's something we are teaching them to do. So connecting counting numbers as a list with cardinality, just putting those things together. I copied this out of your textbook, that's why I put it in quotes. Some of you have already said things that kind of allude to this already. But the last number, you're counting a collection of objects, the last number we say when we count a set of objects tells us the total number of objects in the set. So you have a list of numbers, and then when you come to the end of your list, you counted all your objects, you found the cardinality, you found out how many there are. And it might sound very rudimentary to us, because we're old, we've been at this for a while, but for students, it can take them a while to make that connection of the last number they say is the cardinality of the group. They've counted and they've quantified this amount of things. So in the younger grades, the expectation is that these kids are counting a lot of things all the time, and there's lots of different things to count. And they're usually very colorful and fun. I already mentioned that your book has a lot of activities in it. And we've come to our very first one. Congratulations, everybody. So I'm going to put this up on the projector for those of you that haven't gotten your hands on the book yet. You are going to work with a neighbor. You're going to discuss with a neighbor. So if they have a book, I'm sure they'll like to share with you. But we're going to go to the back section. Let me show you. So the book has a tab like this. We're going to go to the back, and we're going to go to page 2 in the back. And this is what student in the front row, whose name I can't remember, has already mentioned. Tell me what your name is again.
Oh, Cynthia.
Cynthia, she already spilled the beans on this, but she already talked about kids counting a group of things. So this is where we're going to be. This is page 2 in the very back. It looks like this. It's class activities, page 2. So start reading here, and then when you get to the different children, you can discuss with your partner, your neighbor, what you think about those, what those children are up to. I'm going to try to make my book stay down. There we go. Let's go over questions 1 through 4, which is easier, because question 1 and 4 are the same question.
This is the 5th edition, is it?
We saw some common mistakes in it. Several of you have seen these mistakes in kids you've worked with or your own children. So there were some of those in question 2. Here's question 3. We have 2 different children here showing us what they know. So we have this child here. So the first question, how many blocks are there? Question, child 1, and then teacher repeats the question, and there's child 1, and here's child 2. And then hopefully this comparison of these 2 childs is going to help you answer the question in part 1, which is something about the link between the list and the cardinality. Is that true? Yes, maybe.
Cardinality and getting to that and the total.
Oh, that's not. Well, it's close. Question 1 was, if a child can correctly say the first 5 numbers, will the child necessarily be able to determine how many blocks are in a collection of 5 blocks? Why or why not? So, what did you guys say for that? We have several different child's examples here.
Not necessarily. No.
Not necessarily.
Yeah, they might count 1 twice.
Skip it.
And I think it also depends on the order, because some children have better counting from top to bottom than left to right.
That's very interesting.
2, 3, 4, 5, 6, 7, 8, 9, 10. Because you start practicing it with them, or you start teaching it in songs. Oh, 1, 2, and they can't make the connection between the numbers or just things floating in the air until they actually physically touch it or see it, that they can connect to your totals.
Yes.
Yeah, it's kind of like when they're learning their ABCs, and there's children that learn the song, but then when you show them an individual letter, they don't know what letter it is because they just learned the song, they just memorized it. So.
That's I'm glad you said that, because that's actually going to be in the video that we see, which we probably won't have time for. But that's something that they talk about in the video, is that these students have these words in their head, but they don't necessarily know how to read, and they don't know what the word looks like, and they've never had to connect those numbers, those words their parents taught them, with actually using them for a purpose, to find the cardinality of a set. So child 1 maybe knows how to count to 5, but they maybe haven't connected the fact that when you stop on a number, you found the total cardinality of it. So that's the subtle difference for these two. So just because you can count to a number doesn't mean you're prepared to use your superpower to save the world. But you're on pathway.
Right. We said it was kind of like you're on that path, but there's a little gap, and that's where the connection, like building that little bridge, you know. And some kids have little gaps. Like they know the individual concepts, they just can't make the connection, and that's where like the teacher comes in, where you help them build the bridge between one concept and the other.
And people talk all the time about, gaps in my learning, and, they're in 9th grade and they have all these gaps. Well, even very young kids can come in and they don't all know the same stuff, and they have, gaps in the things you might expect them to know at a young age. But anyway, it's funny when you have 3 minutes of class left. Let's see. I want you guys to look at question 5 for the last few minutes, because this is what we're going to see in the video we watch on Monday first thing. So take a look at this. Posing this kind of problem is very common. I can't really get it on here very well. But we have some bears. The teacher says, hey, look at these bears. And then child counts the bears. And then the teacher covers some of the bears and adds an extra bear. So the teacher says, how many bears are there altogether? And we have different responses from different fictitious children. So you want to compare what all these little kids say. So one kid says, oh, I'm out of here. B, child 2 says, counts to 6 while pointing to the covered bears. Then points at the new bear and says 7. And then my book fell on the floor. And finally says there are 7 bears. Child 3 says 6 while pointing to the covered bears, then points at the new bear and says 7, and finally says there are 7 bears. We're going to see this in a video about working with young kids and doing this kind of stuff, but for the last minute and a half here, talk to your neighbor about these different responses and what you think about what children need to understand about the connection between a list and cardinality.
That's very interesting.